Hello everyone, I am Moran Feldman and I am going to talk today about the paper Maximum Matching sans Maximal Matching. This is joint work with Ariel Scharf. In this paper, we consider a data-strip version of the well-known maximum matching problem. In this problem, the algorithm gets the input graph in the form of a stream of edges, and after viewing all the edges, the algorithm should output a maximum size matching of the graph. Now, if the algorithm is allowed to store the entire graph in its memory, then the problem becomes trivial, because then we can simply run our favorite offline algorithm on the stored graph. However, the problem becomes interesting when we limit the amount of memory allowed. One option is to limit the amount of memory used by the algorithm to be polylogarithmic. An algorithm adhering to this restriction is called the streaming algorithm. Unfortunately, streaming algorithms are not relevant to our setting because we are interested in outputting a matching, and a matching might require a space that is linear in the number of vertices. However, we note that if one is only interested in outputting the size of the matching rather than the matching itself, then there are results that are known using streaming algorithms under some assumptions. For example, if the edges of the input graph arrive in a uniformly random order, or the input graph has a bounded arboricity. Given the irrelevance of streaming algorithms for our problem, we consider semi-streaming algorithms, which are algorithms that use a memory that is nearly linear in the number n of vertices in the graph. In other words, we allow the algorithm space of O of n times polylog n. This memory restriction has the advantage that it suffices for storing a solution, or a matching, but it's not large enough to allow the algorithm to store the entire graph unless the graph is very sparse. Thus, the problem does not become trivial. Quite surprisingly, and despite a lot of work that has already been invested in this problem, the only known result for it is an approximation by a simple greedy algorithm. This algorithm starts with an empty solution and then scans the edges as they arrive. Whenever an edge arrives, the algorithm adds it to the solution unless that makes the solution an illegal matching. It's not difficult to see that this makes the algorithm output a maximal matching, and maximal matching is known to provide half approximation for the maximum matching. So far, the half approximation that we have discussed has resisted all attempts to improve it. Therefore, people started to consider relaxations of the problem to get some progress. One option is to assume that the edges of the input graph arrive in a uniformly random order. In this case, there is a known 2/3 plus epsilon approximation. Another option is to allow the algorithm multiple passes over the input stream of edges, rather than just a single pass. If many such passes are allowed, the problem becomes more and more similar to the offline case. Therefore, it is natural to look for algorithms that obtain 1 minus epsilon approximation. The objective then becomes to minimize the number of passes that are necessary as a function of epsilon. There are many known results in this line of work, and you can see some detail about them in the related work section of the paper. In this work, we consider a different relaxation in which the algorithm is allowed only a few passes over the input stream of edges, usually only 2 or 3 passes. In this table, you can see the state of the art for this relaxation. Notice that improved results are known when the input graph is restricted to be either bipartite or triangle-free. Since the objective in this relaxation is to improve over the 1/2 approximation that we know how to obtain using a single path, it is natural to present the approximation ratios as 1/2 plus the improvement. Now, these are the improved results that we obtain. For example, for general graph and 2 passes, we improve the approximation ratio from 1/2 plus 1 over 32 to 1/2 plus 1 over 26. In general, you can see that while we improve over the state of the art in many of the cases, the improvement is unfortunately quite small. Therefore, I would like to talk more about the conceptual contribution of our paper. To the best of our knowledge, all the previous results for few passes, use the first pass only for finding the maximal matching. In other words, they run in their first pass the same greedy algorithm that achieves half approximation in a single pass. Then, in the subsequent passes, these algorithms try to improve the maximal matching obtained in the first pass. While this approach has led us so far, there are some issues with it. First, one of the reasons that we look into multipass algorithms is that we hope that they will lead us to new ideas that can help us get a better than half approximation using a single pass. However, this is unlikely to happen as long as we look at algorithms that start by running the known single pass algorithm. Second, recently it was shown that this technique has its own limitations and cannot obtain better than 2/3 approximation in 2 passes. This suggests that the optimal 2 passes algorithm might have a different structure. We are the first to consider algorithms that do something other than constructing a maximal matching in their first pass. We call such algorithms non-maximal matching first algorithms. If we look again at the table of our results, some of the results in this table are obtained by non-maximal matching first algorithms, while others are obtained using more standard techniques. Specifically, the improved result for 2 passes in general graphs is obtained using a non-maximal matching first algorithm. For 3 passes in general graphs, we also obtained an improved result using a non-maximal matching first algorithm, but we later found how to get an even better result using an algorithm that does construct a maximal matching in its first pass. Now I would like to talk a bit about the standard technique of constructing a maximal matching in the first pass and then augmenting it. Let me remind you what an augmenting pass is. An augmenting pass is a pass that alternates between matching and non-matching edges, but the first and last vertices of the path are not covered by the matching. Given such a path, we can increase the size of the matching by 1 by removing from the matching the edges of the path that belong to it and adding instead the other edges of the path. Thus, if we find a maximal matching in the first pass, then we want to find many augmenting passes in the next passes to get a good final matching. However, when trying to do that, we run into a synchronization issue. Consider the lower graph on this slide. Assume that in the first pass we have greedily constructed this matching. Then, in the next pass, we should extend at least one of the edges of this matching into an augmenting path. This requires us to pick either the top 2 black edges or the bottom 2 black edges. If instead we pick, for example, the red edges, then we get no improvement over the original maximal matching, because these particular edges do not combine to form an augmenting path. In other words, to get an improvement, we must be able to have, at the same time, multiple edges of the same augmenting path. Later, we will see why non-maximal matching first algorithms can help us avoid this synchronization issue. However, I would like to first discuss how we did use the technique of augmenting passes to get a better approximation ratio using 3 passes. Our starting point is a 2-pass algorithm by Kell and Tirodkar. As is standard, in its first pass, this algorithm greedily constructs a maximal matching M. Then, in its second pass, the algorithm constructs a set W of wings. A wing is an edge that connects a vertex covered by the matching with a vertex that is not covered by the matching. The set W is constructed greedily by the algorithm, so that the wings within it cover every matching vertex at most once, and cover every non-matching vertex at most twice. In other words, every time a wing arrives, it is added to W if its addition does not violate these properties. After the algorithm completes the second pass, it constructs as many augmenting passes as possible using the edges of W. To get improved results, we added a third pass to the algorithm. Notice that after the second pass, we are likely to be left with many wings in W that do not intersect any augmenting path that was used. In the example drawn on this slide, only a single augmenting path could be used, because the three possible paths intersect each other, and therefore we are left with the two yellow edges of W. Each remaining edge of W represents a partial augmenting path, and in the third path, we try to greedily complete these partial passes and get further improvement. In the example depicted, this leads to one more augmenting path. Note that we cannot complete both partial augmenting passes of this example since they intersect. This completes the description of our improved algorithm for triangle-free graphs. A more default version of this algorithm obtains our improved approximation ratio for general graphs. We now get to discussing our non-maximal matching first algorithms. Observe that greedily constructing a matching is the same thing as greedily constructing connected components of up to two vertices. In other words, whenever an edge arrives, we pick it if its addition does not create any connected components of three vertices or more. Notice that there are only two connected components of up to two vertices, an isolated vertex and an isolated edge. Given this point of view, it is natural to consider also the possibility of greedily constructing connected components of up to three vertices. This is what our non-maximal matching first algorithms do in their first pass. This allows two additional kinds of connected components, a triangle and a path of length 2. The natural question at this point is, of course, why constructing connected components of three vertices is better than constructing connected components of two vertices. Consider the graph depicted on the left, and the connected components that we have constructed in it during the first pass. Alone, these connected components include only a matching of size 2. However, if we now pick the yellow edge, then we can construct a matching of size 3. In other words, we have managed to get an augmentation using a single edge. In this case, the augmentation was done using an edge that connects two connected components. In other cases, we can also augment using edges that touch only a single connected component. For example, in the bottom drawing, the two left edges represent a connected component containing a single matching edge. However, the yellow edge allows us to augment the size of the matching to 2. The important thing is to observe that in all these cases, we are able to get an augmentation using a single edge, so there are no synchronization issues. Let us now describe our non-maximal matching first algorithm for the case of two passes. In the first pass, as described above, we greedily construct connected components of up to 3 vertices. One can notice that we get all 4 possible types of connected components in the example depicted. Recall that these types are an isolated vertex, an isolated edge, a triangle, and a path of length 2. In the second pass of the algorithm, we greedily construct two sets in parallel. The first set is A1, which includes only augmenting edges touching a single connected component. We make sure to select into A1 at most one edge touching each connected component. The other set that we construct is A2, which includes both augmenting edges that touch a single connected component and augmenting edges that touch two connected components. Again, we make sure that A2 contains at most a single edge touching each particular component. Since the constructions of A1 and A2 are done independently, some edges might belong to both sets. After the second pass completes, the final step of the algorithm is to construct a maximum matching out of all the edges picked in both passes. This completes the description of our non-maximal matching first algorithm for two passes. The analysis of this algorithm is quite technical, and we do not get into it in this talk. Thank you for listening.